COVID-19, an overview. I'll make an attempt at summarizing the salient concepts regarding the understanding of the virology, pathology, diagnosis, and treatment of COVID-19. But given information is changing almost exponentially, some of the information may become outdated, at which time we'll update that information. I implore all of you to stick with the brief discussion because, as we'll see, the science is, of course, incredibly complex and complicated. However, the underlying concepts are relatively intuitive and easy to grasp. So instead of turning off because of the acronyms like SS, RNA, ACE2, PCR, and ELISA, and of course the names of medications, please stick with me for a simplification that will integrate these terms as part of the basic concepts. Also, as with all scientific terms, multiple terms are used for the same thing. I'll attempt to point that out when appropriate. First, what is COVID-19? Well, it isn't the virus, it's the name of the disease. The responsible virus is a specific coronavirus called SARS-CoV-2. Remember that there are many types of coronavirus, including those that cause the common cold. This is not that type. If you don't see SARS in the description, you're not referring to this current virus. The SARS-CoV-2 has a 80% genetic similarity to the SARS virus outbreak in 2002-2003, as well as the MERS, Middle Eastern Respiratory Syndrome outbreak of 2012. And there's a 96.2 genetic similarity between the bat coronavirus and SARS-CoV-2. For that reason, it's believed that the source is the bat. The question then zoonotically is, there an intermediate vector that causes a mutation into the human infection? Well, no one knows. However, for the original SARS outbreak, it was the civet, and in the MERS outbreak, it was a camel. For the current COVID-19 pandemic, it's suspected, though not proven, that it is a pangolin. Why? Because of the suspicion that the origin was in a market where bats and pangolins are sold for food and for mythical healing properties. That's then the intersection of bat, pangolin, and human. Let's compare the case mortality rates for the SARS and MERS epidemics versus COVID-19. We can see that the SARS outbreak in 2002-2003 had 8,000 cases in the U.S. with 800 deaths. That's a case mortality rate of 10%. Then, in the MERS outbreak in 2012, we have 2,500 cases, far less, but around 850 deaths, which equals a 34% case mortality rate. But look at COVID-19. We have, as of May 28th, 1,730,000, with 102,000 deaths, which is a case mortality of only 6%. But look at the numbers. Let's talk about what COVID-19 isn't. It's not due to the coronavirus that causes the common cold, and it's common for individuals who have only a cursory interest in the literature that supports their belief to mistake associations as causes. An example is the large response and then misunderstanding of a recent article that resurfaced a concept related to vaccines. Here's the article: Influenza vaccine and respiratory virus interference among Department of Defense personnel during the 2017-2018 influenza season. Note, the 2017-2018 influenza season, well before COVID-19. Well, anti-vaccination groups are cautioning against the flu shot by falsely suggesting that the vaccine increases the chances of getting COVID-19 by 36%. The study actually looked at 4 types of seasonal coronaviruses that cause the common cold, not SARS-CoV-2. So what is viral interference? Well, here are 3 different but similar definitions. Number 1, viral interference is the inhibition of the multiplication of one type of virus by the presence of another virus in the same cell, a phenomenon which may be defined as protection of host cells against one virus, conferred as a result of prior infection from a different virus. Number 2, viral interference is said to occur when a cell infected by one virus resists superinfection with the same or a different virus. And number 3, viral interference is a phenomenon whereby infection with one virus limits infection and replication of a second virus on a cellular basis due primarily to the release of interferon. Well, first of all, this is a hypothesis yet to be fully confirmed. Ironically, though, when comparing the criticism by those against vaccines, stating that vaccines increase your risk, the concept actually forms the basis for the current vaccine recommendations, which advise to either administer live vaccines concurrently or at an interval of 4 weeks. And the conclusion of this article was that, quote, receipt of influenza vaccine was not associated with virus interference among our population. Examining virus interference by specific respiratory viruses showed mixed results. Vaccine-derived virus interference was significantly associated with coronavirus, not COVID-19, and human metapneumovirus. However, significant protection with vaccination was associated not only with most influenza viruses, but also parainfluenza virus, respiratory syncytial virus, and non-influenza virus co-infections, unquote. Speaking of the flu, many compare COVID-19 with the flu. Many claim that COVID-19 is the same as the flu, in other words, the COVID flu. Well, in the current flu season, the CDC estimates 39 to about 56 million cases, with 24 to 62,000 flu deaths in the U.S., although the number is an estimate based on hospitalizations with flu symptoms. The average over each year is around 40,000 annually, and that's a case mortality rate of about 0.1%. Now, the new coronavirus, COVID-19, has caused more than 1.7 million cases and over 102,000 deaths in the U.S. as of May 28th, according to the data from Johns Hopkins University, with a case mortality rate of approximately 6%. Some argue that the mortality rate is much lower and often quote a study from Columbia University that was recently estimating that only 1 in 12 cases of COVID-19 in the U.S. are documented, partially because as many as 80% are asymptomatic. They said that this then translated into an infection fatality rate of about 0.6%, but that's still 6 times more than the flu. But simply trust what you've seen. Have you ever seen the emergency departments of major cities literally overwhelmed by patients and many in need of ventilation from the flu? Look at the numbers, not the rate of deaths, in Italy, Spain, Brazil, and the U.S. And you don't just compare case mortality rates, you compare the number of deaths in time. So although you might have 40,000 deaths from the flu, that's over an entire year versus the 100,000 in simply a few months. Hardly comparable. So why is there such a huge difference from the beginning of the pandemic to now, when death rates were being proposed in the millions? Modeling took the available evidence, which was basically coming from Wuhan. They also considered other SARS outbreaks in the calculations. The newer calculations are actually calculated backwards using the reported hospital deaths, calculating hospitalizations, and then considering symptomatic individuals. This then led to the 100,000 to 200,000 projection. Secondly, the initial calculated numbers were without modeling for changes in social distancing and other enforced rules by government. Let's look, though, at why calculations can never be accurate as an average. There are 2 parts to the rate of transmission, R0 and series interval. R0 is the reproductive rate, which is simply how many individuals can one individual infect. Well, for COVID-19, it's estimated somewhere between 2 and 3. We're going to use 3 to demonstrate the effect. One individual would first infect 3 individuals, who would then infect 9 individuals, who would then infect 27 individuals. We can see here what looks like exponential increases with an R0 of 1, leading to about 12,000 infections within 60 days and up to 25,000 infections with an R0 of 1.1. But this is with no intervention to prevent spread. Nobel Prize-winning Stanford professor Michael Levitt, using artificial intelligence and machine learning modeling, doesn't feel that the spread is likely to be exponential given the data from other countries and the rapid drop-off of new cases. And what has to be taken into account is the individual country's response to the pandemic, because the R0 number isn't fixed, but can be affected by a range of factors, including not just the infectious disease, but how it develops over time, how a population behaves, any immunity already possessed, or vaccination. There's also the location. A densely populated city is likely to have a higher R0 than a sparsely populated rural area. If you dropped an infected individual in the middle of New York City versus a rural area in Montana, your R0 is clearly influenced, magnitudes of difference. And transmittability is the feature of R0 that takes into consideration the average contact an individual has with others, which then doesn't apply to a recluse individual compared to a partygoer. So the R0 can't predict for all areas, and it's literally contextual and dynamic. And remember that R0 is only part of the equation. The other is called series interval. The series interval is simply the time it takes to pass the disease to another individual. And for COVID-19, it's estimated to be about 4 days. So if this is a true estimate, then it would result in a sum of the R0 numbers, 1 plus 3 plus 9 plus 27, which equals 40 individuals infected in 12 days. But again, there's a problem. Asymptomatic individuals make up the majority, so that it makes this calculation very difficult to rely on without further data from widespread testing. Perhaps it comes down to an illusion, because everyone is used to there being a correct and incorrect answer to an equation. So when they see numbers from statistical modeling, they assume the same. But unlike an equation that needs to be solved with all factors known, statistical modeling approaches from a proposition of if this is true, then this may happen. And furthermore, the best that can be usually done is an average across a large population and perhaps a range. We're certainly all familiar now with the modes of transmission, but mainly it's through respiratory droplets, which may aerosolize up to 3 hours. Also, there's a potential of fecal-oral transmission, and also it's unknown, but the possibility of vertical transmission from mother to fetus. Initial shedding by asymptomatic people may represent about 25 to 50% of total infections, and viral shedding may antedate symptoms by 1 to 2 days. And then, of course, the less likely but still potential of fomites from aluminum, cardboard, plastic, and wood. Let's move on to the pathology. Here's the general viral structure. There are surface proteins, including a spike protein, hemagglutinin esterase protein, M protein, E or envelope protein, and the nucleocapsid protein or N protein. And then there's the non-structural genetic proteins, often referred to as positive sense single-stranded RNA. Let's look at the sequence. Via the spike protein, the virus binds to ACE2 and transmembrane receptors. For entry into a host cell, its S protein needs to be cleaved so that it will fuse and then through endocytosis pass into the cell. The vesicle then uncoats from the viral envelope. Positive sense single-stranded RNA is released into the cytoplasm. It then binds to lysosomes. 2 processes occur with the single-stranded RNA. It's used to construct structural and non-structural proteins, which are subgenomic material. For structural proteins, the ssRNA is translated into proteins to make the virus spike proteins and other structural proteins. Also, RNA-dependent RNA polymerase is created to translate and construct more COVID RNA. All are then transported into the Golgi organ, glycosylated, and then the viral capsid is assembled into a new virus and released into the cytoplasm. The lipid bilayer of the virus fuses with the cell membrane of the host cell and through exocytosis releases the virus. So why the lungs? ACE2 receptors are on multiple organs. However, the major concern is the lungs, because ACE2 is normally protective of lung function. Spike proteins bind to the ACE2 receptors specifically at type 2 pneumocytes, leading to downregulation. However, ACE1 enzymes now compensate with overproduction of angiotensin II, but that increases vascular permeability that impairs oxygen exchange and leads to alveolar edema. Recall that type 1 pneumocytes are the alveolar epithelial lining necessary for oxygen and carbon dioxide exchange and are unable to replicate if damaged. In the event of damage, type 2 cells can proliferate and differentiate into type 1 cells to compensate. There are some protective responses, but also damaging responses. Damaged alveolar type 2 cells release interferons. This signals healthy alveolar cells to manufacture antiviral peptides and damage-associated molecular patterns, or DAMP, and inflammatory cytokines. This is somewhat protective. However, let's review the resulting cytokine storm and its consequences. Damaged cells also activate alveolar macrophages, which then secrete inflammatory mediators like interleukin-1, interleukin-6 and 8, and tumor necrosis factor alpha and gamma interferons. Interleukins and tumor necrosis factor move into the pulmonary capillary area, causing endothelial cells to open, resulting in fluid leakage into capillary spaces, causing interstitial edema, and some may move into alveoli, causing alveolar edema. This thickens the alveolar capillary walls, making gas exchange more difficult. This will then lead to hypoxia. Interleukins 1 and 6 and TNF increase expression of certain proteins, including VCAMs, or vascular cell adhesion molecules, which direct WBCs to the alveoli, perpetuating inflammatory processes. Neutrophils activated by interleukin 8 release reactive oxygen species and proteases. Damage to type 2 alveolar cells leads to a decrease in surfactant, which decreases surface tension, causing alveolar collapse. And cytokines can increase the production of procoagulants and decrease anticoagulant activity, leading in particular to pulmonary emboli. Inflammatory cytokines include leukotrienes, bradykinin, prostaglandins, and these can activate receptors on the vagus nerve, generating a cough reflex, a non-productive cough. And leukotrienes act on smooth muscle, leading to bronchoconstriction. This can all result in ARDS, and this is due to upregulation of a pro-inflammatory cytokine and chemokine response. But why do some develop acute respiratory distress syndrome and some not? Patients who recover seem to have an early and strong response with the production of both interferon alpha, which is antiviral, and it's released by the infected cell. It also signals to the other cells. And then we have interferon gamma, also antiviral, but it's released by immune cells.